Hello students, in this video we'll begin our discussion of linear fractional transformations. Let's be given A, B, C, and D complex numbers and consider T of Z is AZ plus B over CZ plus D. These transformations, these mappings, are called linear fractional transformations. Or LFTs for short. And sometimes in other books, in older books, they're called Mobius transformations. Okay? We're going to need one sort of special condition. I'm going to assume over here, that AD is not equal to BC. Okay? Now you might say, why am I making this assumption? Let's think of a simple case. If A, D, B, and C are all equal to 1, then I have Z plus 1 over Z plus 1, I get it 1. I get a constant, right? So in other words, in the case when AD is equal to BC, AD equals BC implies that T is a constant. Okay, and constant functions are okay, they're just not interesting, right? All right, so we're going to assume that AD is not equal to BC. Now, there are some important things to understand about these linear fractional transformations, so let's do this, some of the most elementary properties first, okay? So what's the first elementary properties? What are some properties of LFTs? We'll get to more advanced properties in further videos. What are properties? Property number one is that if I look at T, for example, of what? If I look at T of negative D over C, T of negative D over C, if you plug in negative D over C, what will happen in the denominator here? You're going to have a negative D and then a positive D. That's going to give you what? That's going to give you infinity, right? So this T is going to map the point negative D over C to positive infinity, okay? And now, remember, we're thinking of positive infinity as a point on the Riemann sphere, so there's a natural identification, right? So I'm thinking of T as a mapping from the Riemann sphere. So in other words, what we're thinking of T mapping the Riemann sphere onto the Riemann sphere, right? In other words, so infinity is a permissible value because that's just the North Pole, right? Okay? And T of what? And T of, I'm going to put infinity now, meaning the limit as Z goes to infinity. Well, as Z goes to infinity, it goes to A over C, right? Excellent. So I know that infinity gets mapped to A over C, and I know the preimage of this is negative D over C. Okay, that's beautiful, right? Now, let's investigate some of the invertibility properties of this thing, right? So if I was to say, if I look at W, what's W? W is going to be AZ plus B over CZ plus D. Then this tells me that CZW plus DW is equal to AZ plus B, like that. Good. And then if I solve this equation for Z, what will we have? We'll have, this is going to be a CZW, and then minus AZ is going to be equal to what? It's going to be equal to B minus DW, like that. Okay? And that tells me what? That tells me that Z is what? Z is going to be B minus DW over what? Over what? I'll have a, I'm solving for Z, so I'll have a CW minus A. W minus A, like that. And lo and behold, this also is the structure of a LFT, right? So if I look at this function over here, so what we can say, therefore, is if we say that if I define S of Z to be what? S of Z to be negative D W plus B, or negative DZ, sorry. That's a Z now. We're going to change it to our Z variables. Negative DZ plus B over CZ minus A. Then what do I know if I do these? This is also a what? This is also an LFT. And moreover, it's what? It's the inverse of this mapping T. And moreover, S is equal to T inverse, right? And so in particular, what do we know? If I let z go to infinity, what's happening is z goes to infinity, I get negative d over c. Oh, look, it's exactly as the property I want. So in other words, if I plug in s of infinity, I get negative d over c. If I plug in what? If I plug in a over c, I get infinity, right? So it interchanges these roles over here, right? So in particular, s of infinity is equal to negative d over c, and then s of what? And then s of a over c, in this case over here, a over c is equal to infinity, right? So it swaps the rules of infinity and 0, and every other point in the Riemann sphere gets mapped to a unique solution over here, right? Because that's a unique value. So in other words, t is invertible as a bijection of the Riemann sphere. So all this property over here says that t maps c hat into c hat is a bijection. It's 1-to-1 and onto. Great. So c is a bijection of the unit sphere. Excellent. Now, what's the next property we wanted to prove? The next property we want to prove is that, in fact, it forms the collection of LFTs forms a group with respect to this composition, right? And so here's a proposition. The collection of LFTs now, I have to be a little bit careful because, of course, I can multiply top and bottom by lambda, and that won't change anything, right? So in other words, the choice of these coefficients a, b, c, and d are not unique. So I have to mod out by basically, so I'm going to sort of sweep this algebraic issue under the rug, because technically I have to look at a quotient set modulo all complex dilations, right? But I don't want to have to do that just yet, okay? So the collection of LFTs, so if you want to investigate that, it's a good sort of thought exercise for those of you who've had some group theory or some more abstract algebra. You say like, well, wait a minute, the set of LFTs, when I say set of LFTs, if I give you an LFT, there's actually an infinite parameterized family with every complex number that generates these LFTs, right? So I have to choose one of the representatives, right? And so I can do that in a unique way via a quotient set, okay? The collection of LFTs is a group with respect to composition, okay? So good. So what happens if I have two LFTs? So in other words, let me plug an LFT into an LFT and see what happens, right? So if we plug an LFT into an LFT, so let's look at, here's the proof of this proposition. Okay, so if I have two LFTs, so if I have T1 of Z, which is A1Z plus B1 over C1Z plus D1, and then let me put i's here. So if I have Ti, I'm going to put an I, and then an I, and then I, to save some marker space, right? Do my environmental stewardship for the day by putting an I there, right? For I equals 1 and 2. I equals 1 and 2. Then let's look at T1 composition T2. T1 composition T2 of Z is going to be A1 times A2Z plus B2 over C2Z plus D2 plus what? Plus B2 or B1. Now, of course, with the B1, what I'm going to do is I'm going to fill in this thing over here. So it's going to be B1 times what? Times C2Z plus D2 over C2Z plus D2, all divided by what? All divided by C1, and then A2Z plus B2 over C2Z plus D2, plus finally a D1 times what? C2Z plus D2 over C2Z plus D2. Whew, that's a lot of writing, right? But notice, of course, that all of these things are going to simplify, right? Because everything now is a common factor of what in the denominator? Has a common factor of this C2Z, D2, C2Z, D2, right? They're all the same, so all those things are going to cancel out, right? And you're just left with what? You're just going to be left with, if we summarize this, we're going to be left with A1 times A2Z plus B2 plus B1 times A2Z plus, sorry, C2 rather. We have to keep those C's somehow, right? So those are going to be the C2 terms, C2Z, C2Z plus D2, all divided by what? All divided by C1 times A2Z plus B2 plus what? Plus D1 times C2Z plus D2, right? And so now what the top is what? The top is affine, is an affine mapping, over the bottom is an affine mapping. So affine over affine is an LFT, right? So this is an LFT. Okay. So what I've shown so far is I've shown that with respect to composition, this of course is composition. That is the composition symbol, right? I know it's closed under composition. Good, that's the first thing we need. I know that an inverse exists from this previous proposition. That's inversion, right? Think about what the identity is, right? The identity over here, your identity, LFT, is just going to be Z, right? And then the only thing I've yet to prove, which I will leave to you all because it's just a lot of sort of writing down and it would basically can take up the entire board of just writing, is to prove that the group with respect to composition is associative, right? So that's the last part of this. So also note, so it's easy to see, it's trivial to see this relationship is true. So in other words, if we look at this expression over here, if I look at, let's do it carefully, the last thing to show is that T1 compose T2 compose T3 is really the same as T1 compose T2 compose T3, right? That's not difficult to prove, right? It's a good exercise for you to sort of get a handle on how the LFTs work over here, right? What we're going to do next in the next video is we're going to examine further properties of LFTs, right? So what we've shown so far is we said, okay, really these LFTs are a bijection from the Riemann sphere to the Riemann sphere, and they form a group with respect to composition. Now what we can do now is we can follow two branches. We can follow the question of interpolation, how we can use LFTs to interpolate any 3 points on the unit sphere, right, or the Riemann sphere. Or we can say, okay, well, there's some sort of group structure. Can I identify that group structure with a commonly known group structure, right? In other words, and we'll be able to do that in terms of identifying these LFTs with matrices, and we'll see how there's a natural isomorphism between the class of LFTs and the class of matrices, complex valued matrices, 2x2 matrices of a certain form with a certain invertibility condition. So that's like a general linear group, sort of an isomorphism over here. And so it should be clear from the structure that there's an isomorphism between the set of LFTs and the set of generalized linear, the set of invertible matrices 2x2 with complex entries, and we'll see that in further videos. Thank you very much.